So in the next few videos and lectures, we're going to discuss a few special types of filters. These filters are commonly used in theoretical and practical applications of signal processing. And one of them we have already seen when we conclude chapter 6. So this first one we're going to discuss is called the Butterworth filter. It's come from chapter section 7.5 of the textbook. So Butterworth filter is a filter, meaning we have to quantify that with transfer function, as it has no zeros. It has n poles for an nth order Butterworth filter. So we usually say this is the second order Butterworth filter, third order Butterworth filter, and so on. And the order of the filter is equal to the number of poles in the transfer function. So the arrangement of the filter is like this. Sorry, the arrangement of the poles will be like this. It depends on whether or not n is an odd number or even number. Let's first look at the odd number scenario. That's when n is equal to 1, 3, 5, and so on. Okay. So again, let's say we have our complex plane. The filter must be asymptotically stable. And if n is odd, it must have a pole at -1. And the rest of the poles must be on the unit circle. Okay? Of course, in this case, the semicircle. And the poles are uniformly located. There have to be a total of n poles. I'll use a different color to show where they are. All right, so the angle that separates each pair of poles exactly equal to pi divided by n. Same here, pi over n, pi over n, pi over n, and so on, and so on. So if we do this, you have a pole at n equal to -1. You should have n minus 1 over 2 poles above the real axis and n minus 1 over 2 poles below the real axis, since you have each one of them has to have its complex conjugate. Okay, and there goes the case where n is an odd number. If n is an even number, the story is similar but not exactly the same. When n is even, all the poles are still uniformly located on the semi-unit circle. And the poles each pair of poles are still separated by pi over n. This is pi over n. Right? So this angle is still pi over n. And since they're symmetric, right, if you only look at half of the circle, and half of the angle here is actually pi over 2n. So this is the arrangement of the poles when n is an even number. In this case, you have half of n poles on top, the other half below the real axis. Right, and it's not difficult to find out the general equation to put together all the poles nicely. Okay? And the book has summarized that equation. Um, Now, this is the case where we call the filter a normalized Butterworth filter. Since all the poles are on the unit circle, right? And we'll start looking at the Butterworth filter by focusing on this normalized version, and then we'll discuss how can we extend this to a more general scenario. Okay, so let's look at these from n equal to 1. That will give us a first order Butterworth filter, right? And since in this case n is an an odd number that falls to the left scenario, and for that case you are guaranteed to have a pole at -1. And since it's a first order system, that's the only pole you have. H of s equal to 1 over s plus 1. And the magnitude of its frequency response, it's not difficult to find out. It's going to be 1 over square root of 1 plus omega square. Okay, let's do n equal to 2. So this is called a second order Butterworth filter, and we'll look at it in the normalized version. So n equal to 2, that means you have one pole on above the real axis, one pole underneath, and n pi divided by 2n, n equal to 2 before pi over 4 is 45 degrees. So we know that the two poles are actually here and here, 45 degrees here. So what does it mean? That means the two poles are at negative square root over 2 plus minus j square root of 2 divided by 2. So these are the positions of the two poles that can be easily find out as long as you figure out, oh, these are the two poles. And h of s, the transfer function will be equal to 1. There's no zeros, always 1 on top. And s squared plus square root of 2 times s plus 1. All right. So the sum of the two poles with a negative sign will become the coefficient in front of s. The product of the two poles will give you the constant term. So this is the property of the roots of the quadratic equation. And if you just plug in the two roots, you'll have the exact same uh, characteristic polynomial. Now h of j omega can plug in the numbers. So 1 minus omega squared plus j square root of 2 omega. So the magnitude will be 1 divided by square root of 1 minus omega square plus 2 omega square. And if you organize the term, you will quickly find out it's 1 over square root of 1 plus omega 2 to the fourth. Since the negative 2 omega square from the quadratic calculation, and the plus 2 omega squared will cancel each other. So end up with just 1 plus omega to the 4th. Right? Just the second order. And you can already see some similarity comparing the frequency response function, the first order, and the frequency response function of the second order Butterworth filters. We can go one step further, and the third order Butterworth filter is the one that we have discussed earlier when we had the circuits with 2 inductors, 1 capacitor, 1 resistor. Right at the end of chapter 6 and beginning of chapter 7, we've done it already. Let's say third order Butterworth filter. The poles guaranteed to have 1 here and -1, and pi over n will be the angle separating each pair of them, so it will be 60 degrees. That's pi over 3. And S1, 2, 3 will be -1, and -1/2 plus minus j square root of 3 over 2. And we have done this already, so I'll directly go into the transfer function, which is s cubed plus 2s squared plus 2s plus 1. And the frequency response function, the magnitude is 1 divided by square root of 1 plus omega to the 6. Again, although the transfer function may take some different uh, appearance, if you look at the frequency response function, you will see the similarity directly from the first order case to the second order case to the third order case. And in fact, this can be extended to a general nth order polynomial, or the nth order Butterworth filter. Of course, again, we're in the normalized version of it. Its frequency response function can always be written in this way: 1 over square root of 1 plus omega raised to the 2n. And you can see how convenient this will be to have a Butterworth filter and look at just the frequency response function. Right? And if we observe all cases from n equal to 1 to n equal to 2, n equal to 3, and n equal to n, you can always find out something, right? For any scenario, h of 0 is equal to 1. And h of j omega, or omega equal to always equal to square root of 2, sorry, equal to 1 over square root of 2. And this is what we discussed earlier. This is our half power frequency. Because if here you square this h, the magnitude, you have exactly 1/2. And that's the modulation of the power of the signals from input to the output of the filter. So that means for a normalized Butterworth filter, no matter which order it is, the DC gain will be the same. The half power frequency is the same at omega equal to 1. Now we can sketch the frequency response function as a function of frequency omega. So we know always start with 1, and when frequency is equal to 1, square root of 2 over 2, so about 0.7. So all the Butterworth filters in the normalized fashion must pass through these 2 points. Of course, the difference is how these two dots are being connected. Now draw three curves. And of course, the red curve appears to have a more flat behavior in the low frequency range and sharper drop from the high magnitude to the low magnitude. And it's not difficult to find out that if we assume this is n equal to 1, 2, 3, it's n equal to 3, green curve n equal to 2, and we can say this is n equal to 1. The higher order you have, although they pass through these 2 points perfectly, higher order will lead to a flatter behavior in the low frequency range before the half power frequency and a sharper drop around the half power frequency. Meaning if you can choose a higher end, the behavior of a Butterworth filter, higher order Butterworth filter, will approach the appearance of an ideal low pass filter better. However, as we mentioned, higher order of a filter indicates that it's going to require more resources. The number of filters, the order of the filter is equal to the number of characteristic roots in a polynomial. And in circuit language, the number of roots or the order of the system is equal to the number of energy storage components, meaning inductors and capacitors. So for a second order system, you need two components, like two inductors, two capacitors, or one inductor, one capacitor. Third order, as we have seen in the example, you need two inductor and one capacitor, three components in total. When n becomes larger, you need more and more components, which will add to the complexity of the device, and will add to the cost, complexity of the overall system as a whole. So there's always a trade-off, and people can decide based on their application where you want to go as far as the order of the filter is concerned. And this is one of the parameters you need to choose, you need to select in the design stage. So this is the normalized fashion, right? What about you don't want the half power frequency to be equal to 1? And that's easy. In a general version where the desired half power frequency is not equal to 1, but equal to, let's say, omega sub c. Then what you need to do is replace the S term in the normalized Butterworth filter with S divided by omega c in the transfer function. And that means, let's say if you have n equal to 1, the transfer function will be 1 over S over omega c plus 1, right? Frequency response function, the magnitude, is 1 over square root of 1 plus omega over omega c squared. And let's say if you say this is n equal to 2, let's do another example, n equal to 2. Transfer function will be S over omega c squared plus square root of 2 S over omega c plus 1. And the frequency response function as a result, it's just a simple substitution. Right, this substitution from S to S over omega c is sometimes called frequency scaling. Okay. And of course, if we generalize it to in the nth order scenario. Although the transfer function could be more complex, the magnitude response function is pretty simple. 1 plus omega over omega c to the power of 2n. To the power of 2n. And in this case, when you draw this frequency response function again, start with 1, square root of 2 over 2 is here, half power frequency is omega naught, omega c. And the curve will look like this. And as we mentioned, it's easy to find out that if you take the derivative of the frequency response function, the magnitude frequency response function with respect to omega, meaning you want to look at the slope at the beginning of this curve, it will be equal to 0. Meaning in the low frequency range, when this frequency response function starts, the slope is 0. And not only that, because the special appearance of this curve, you can take this derivative k times. And for k equal to 0, sorry, k equal to 1. K equal to 1, 2, up to 2n minus 1. This derivative term is always equal to 0. Okay? Meaning the slope of this curve at the beginning is flat. The slope of the slope is also flat. That's the second derivative. And the slope of the slope is also flat. This is what we call maximally flat. And this is a nice, desirable feature of the Butterworth filter, right? When you have a low-pass filter, when you want to appear close to what an ideal low-pass filter is, you want the passband to have a flat magnitude equal to 1. And this slope thing, at least at the beginning, can guarantee that's happening.